Imagine a platform that is serving over 500 hours of video content every minute and also serving 2 billion users worldwide. And this is not just a video sharing website, but it is highly complex and scalable system that is ensuring millions of video streams seamlessly every second. And yes, here we are talking about YouTube. Hi, I am Vishaka, and in today's video we are going to learn about the system design behind one of the largest video platform, that is YouTube. This video is going to be breakdown that is going to give you the key insights of the YouTube's architecture. In this video, we are going to mainly talk about the video upload system and video streaming system. Then we will talk about the scalability of YouTube, how YouTube scales to billions of users worldwide. Then we are also going to talk about content delivery networks, basically CDNs. And we are also going to talk about how YouTube manages to scale to the billions of users worldwide while also ensuring availability to the users and even low latency. Before we dive into these functionalities, let's first take a closer look at the core features of YouTube. So the first one is going to be the video upload. So when users upload their video to YouTube, suppose this is the YouTube systems, okay? So this YouTube system has to handle several things simultaneously. It has to accept the wide range of formats. If I say formats, I mean by like MP4, MOV. These are the formats that YouTube has to accept. These are just not only the formats, there are many more. YouTube also has to accept different resolutions. So some content creators might upload their video into 360p, 420p, and even some might upload it to the 4K. So YouTube has to accept this wide range of resolutions too. So the YouTube's backend or server has to convert those files which the content creators are providing into the consistent and streamable format, and this is going to be known as video transcoding, and we are going to talk about this in detail later on. And once the video has been uploaded by the user to the YouTube, then YouTube needs to also compress it into multiple resolutions, which I already told you, like into 144p, 360p, 720, and even 4K. And this is going to ensure that the different internet speed can stream the video smoothly. And this is done through bitrate streaming, or we can say adaptive bitrate streaming, ABS, which basically adjusts the video quality based on the viewer's connection. And once the video has been processed by the YouTube and has been converted into the different formats, or you can say it has also been compressed to different resolution, it becomes available for streaming. So users can stream the video too, but streaming a video to millions of users simultaneously is no small task. So what does YouTube do is it uses CDNs. Now, what is CDN? A CDN is globally distributed network of servers, and it is done to deliver the videos quickly and efficiently to the users based on their geographical location. And this CDN ensures that when user click on the play button on the video is served from the server that is closest to the user. And this is going to reduce the buffering time and even the latency. And this allows YouTube to scale and serve high quality videos to millions of concurrent users without overwhelming their servers. And if we dive deep into the CDNs, I am bad at drawing and I know that, so let's just keep that aside for now, okay? So if we dig deeper into the CDN, what YouTube does it caches the copies of video across multiple locations worldwide. So let's assume this is a world map. And now what YouTube does it caches the copies of video across multiple locations. So suppose for this video, which you are streaming right now, has been cached into the America server, has also been cached into the Africa server, Europe's, or Asia or Australia. And now, in this way, if the user is watching a video in India, they are not requesting the video from the central server that is in America, but from the nearby data center which is present into the Asia. So basically, they are not hitting the America server, they are hitting the Asia server which is nearby to them, okay? And what it does, it massively reduces the load on YouTube's original server, and it also ensures the low latency delivery, also improving the user experience. So I hope now that you understood what are CDNs and what it is used for. And now another core feature of the YouTube is search and recommendation. So let's talk about the search and recommendation. These are the two core features that powers the user's discovery on YouTube. So basically, suppose this is YouTube's website. Over here you have this video, and at the top you also have like a search button. So suppose over the search you are searching for the system design of YouTube. YouTube system searches quickly through the billions of videos, leveraging its search indexing system, which is going to ensure that the relevant content appears almost instantly. So like when you're searching for system design of YouTube, so that videos would appear, and YouTube is not going to give you the search recommendation for a cake, how to bake a cake. Of course, what you searched for, you search for system design video. So yes, YouTube utilizing its search indexing feature, it is only going to show you the relevant content. And on the other hand, we also have the recommendation system, and when you go to the YouTube's website, you also see that there are relevant videos to you, right? And this is different for every users. YouTube's recommendation system is powered by machine learning models. It analyzes the user's behavior, it uses the video metadata, it also uses the watch history of a user, and it is also going to suggest the videos that the user mostly likes to enjoy. So every time you go onto the YouTube, you will see that the videos that has been recommended to you are the videos that you likely enjoy. So these recommendations have to be tailored in real time, as YouTube processes massive amounts of data from billions of users, okay? And then we have the user's interaction, fifth core feature, and over here I am talking about the like, comment, subscriptions, okay? So every time on the YouTube you see a video, you particularly like a video, suppose you dislike a video, you subscribe to the channel because you like their videos, then there are also the comment section if you want to comment onto their video. So YouTube needs to record these interaction and process them in real time, and these actions are stored and updated into the database. That database must handle millions of interaction per minute, because we are not just the ones who are watching the video. There are millions of people out there who are streaming some or the other video right now, okay? So let's take for an example, if a video suddenly goes viral and it is getting the thousands of likes and comments in few minutes, so the YouTube system needs to be designed into a way that handles the search in activity without slowing down or crashing. So now that we can see, the core features of YouTube's are going to be the video uploading, streaming, CDN, search recommendation, and users interaction. And these are all backed by some of the complex system that is working behind the scene, and it is ensuring that we have smooth, scalable, and personalized experience. So now that we have the good understanding of the YouTube's core feature, let's go ahead and understand the underlying architecture that supports these functionalities. And before we move ahead, I'm just going to tell you this one thing, that in this video we are not going to particularly talk about this user interaction or about the search and recommendation. Yes, we are going to talk about the CDNs, we are going to talk about the video streaming, adaptive bitrate streaming, and we are also going to talk about the video upload. but we are not going to talk about user interaction and search and recommendation into this video. Let's go ahead and talk about the functionality of YouTube. So over here, we are going to talk about the functional requirements of YouTube. So for us, the functional requirement would be the first, that is video upload, because we want to upload the video to YouTube, right? And YouTube also needs to allow the users to upload the video into various formats and even different resolutions. So the key functionality over here is going to be process the video for adaptive streaming, adaptive bitrate streaming. Now let's talk about the video streaming. Now this is one of the YouTube's critical feature, and it is also an important one, right? Because YouTube needs to stream millions of videos simultaneously to the users across the globe. And YouTube system must provide the smooth streaming, and how it does it by delivering the video in real time with minimal buffering, and this is done through ABS, adaptive bitrate streaming. So the functional requirement over here is going to be reliable, fast, and it should be scalable. And now yes, these are the two functional requirements. So let's now talk about the non-functional requirement of YouTube. Now these non-functional requirements are going to be like the qualities that ensure the platform not only works but works well, okay, even under the immense scale and pressure. And these non-functional requirements are very important to deliver a seamless experience to billions of users that YouTube have. So the first one over here is going to be scalability, and this is one of the most important for a platform as large as YouTube. And YouTube must handle the increasing number of users, videos, and even the interactions. And from a few user watching a viral video to billions of users that are concurrently streaming some different kind of videos across the globe, this YouTube system needs to scale horizontally. And why horizontally? We are also going to discuss this later on in detail. And with horizontally, I mean as the user base, it is growing, right? User base is growing. YouTube should add more servers. YouTube should add more servers and even the data centers and resources without the decline in performance. Because this is something that user won't like. If the performance of YouTube was not good, you would not be watching video right now on YouTube. And this all is achieved through distributed system. You are also going to need load balancer for load balancing, and we are also going to leverage the some cloud infrastructures that scales on demand. And the second one is going to be reliability. And right now at this moment, millions of users are accessing or streaming video on YouTube, and the platform for this must perform 99.9% of the time, and this is referred as highly available. So to ensure the reliability, YouTube system is designed with redundancy at every layer. Yes, at every layer, whether it is the data stored into multiple geographical regions or we are talking about the servers. They all have a backup system ready to take over in case of failure. So if some data center is failed, the other data center of the YouTube will take over, and this will prevent the failure. So here what we will have, failover mechanism. We will also have data replication. We are replicating the data across geographical region, and geo redundancy. And the non-functional requirement is also going to be the performance. YouTube goal is to deliver fast and seamless experience regardless of whatever the user's device or location is. And this means low latency for video playback and fast video loading time and smooth streaming. And to achieve all of this, what YouTube does it uses a technique like edge caching. So this means where the videos are stored onto the server close to the user through CDNs, and this will reduce the distance data has to travel, okay? And not only the CDNs, but YouTube also uses video compression algorithms. And what this does it reduces the file size while maintaining its quality, okay? And yes, that is what we are going to have for the non-functional requirement of YouTube. Let's now move on to the back of the envelope estimation, which will give us the rough calculation to understand the scale and the capacity YouTube needs, okay? This back of the envelope estimation will help us better understand the amount of the data YouTube needs to handle and the infrastructure it requires. So, first of all, we will start with the total number of users that YouTube have and what are the daily active users. So here we are assuming that the total number of users that YouTube have is going to be 2.5 billion, of course globally, and for the daily active users we typically say like 35% to 50%. So for the daily active users of YouTube, let's suppose we have 35%. So if we calculate, we have to do it like this: 2.5 billion. We will multiply it by 0.35 because we have converted the percentage, and this will nearly equal to 875 million DAU. Then second thing we calculate is size of an average video, and this we are doing before the processing or before encoding. So PE, I mean like processing and encoding, okay? So let's suppose before processing, a 1080p raw format with no compression is like a 1 hour of video is generally much larger because of its higher bitrate. It's nearly about 10 to 20 GB, and we are saying 10 to 20 GB per hour. So let's assume the average size of the video before encoding is 15 GB per hour. Let's now calculate the size of an average video after encoding. So after encoding and compression, a 1 hour long video, which is like 1080p, will take up nearly about 1 GB after the compression and the processing has been done. So we say the average size of the video after encoding is 1 GB. Okay, and now if we want to estimate the daily video views, we are saying it before encoding. So here we assume that 500 hours of video has been uploading to the YouTube per minute. So 500 hours into 60 minutes, like for the 1 hour, this will approximate to 30,000 hours of video is been uploading per hour to YouTube. And if we calculate it for the day, let's say 30,000 hours per hour multiplied by 24 hours, and this will approximate to 720,000 hours of video per day. In Indian system we say it like 7,20,000. Okay, so before encoding, let's say 720,000 hours multiplied by 15 GB. We are doing it before the encoding. This will approximate to 10.8 million GB, and if we convert it, this will approximate to 10.8 petabyte. So for like million we have like a 6 zeros, okay, and for GB we have 9 zeros. So when we plus it, we get it into the petabyte, so which is 10.8 petabyte, okay, before encoding. But after encoding, let's say 720,000 hours multiplied by 1 GB after encoding and compression, this will near about to 720,000 GB, and if we convert it, this will get to 720 terabyte, because GB is like 9 zeros plus 3, which is like 12, so terabyte for that, okay? And this is in a single day, okay, per day. So this is for the daily video views. Now let's calculate the daily. So this was the daily video uploads, not views. I'm so sorry for that. And now we are going to calculate the daily video views. So now we will estimate the number of the video views YouTube handles daily. So we are saying over 5 billion video views each day. And on an average, each view we are saying lasts for 5 minutes. So the total viewing time per day would be like 5 billion multiplied by 5 minutes, and this will approximate to 25 billion minutes watched per day. And now to convert this into the hours, so 25 billion, yeah, whatever this is over here, divided by 60, and this would approximate to 460 million hours of video per day, watched per day, okay, watched. And the data transfer per day, we are supposing that 2 Mbps multiplied by 416 million hours would approximate to 832 million Mbps. And if we convert this Mbps to GB, we would have like 832 million Mbps. We will divide it by 8 and divide it by 1000, and this will approximate to 104,000 terabyte. So this is the data transferred, and this is per day, okay. And now if we calculate the storage estimation, so storage per day would be 720 terabyte multiplied by 5. This would equal to 3600 terabyte per day, and for per year we will say 3600 terabyte per day multiplied by 365 days, and this would approximate to 1.3 million terabyte. So this is the storage estimation. And now we will also calculate the last one, that is the bandwidth, not the last one but the last second. And now to estimate the total bandwidth YouTube needs daily, we are going to use the calculations like 104,000 terabyte multiplied by 1000. This is to convert it to GB, and multiplied by 8 to convert it to Gbps, and this would approximate to 832,000 Gbps per day. And now you can even convert it to TBps. You just have to remove the 3 zeros. It would be 832 TBps, terabyte per second. And this is the bandwidth YouTube will need to serve all the video streams globally, okay. And last but not the least, which is server requirement, because we need to calculate the servers too that we will be needing. So the server for 1 day upload, we are assuming that we have 720,000 Gbps. So this is like the video uploaded per day divided by 100 terabyte per server. Okay, we are assuming this, and this would nearly give us 7,200 server needed just to store single day's worth of YouTube videos. And we had like a 1.3 million terabyte of storage per year, right? And we would divide it by the 100 terabyte per servers. We would approximately get 13,000 servers per year. Okay, so these are the back of the envelope estimations for YouTube, and these estimations just shows us that how massive the YouTube's infrastructure has to be to support millions of uploads and billions of views daily. So this is what we are going to have for the back of the envelope estimation. And let's now look into the different approaches to building these core components of a system like YouTube. So we will be focusing on if we want a monolithic or a microservice architecture. So let's first talk about the monolithic architecture. This is referred to as unified code base, where all the functionality of the system have been tightly integrated into the single application. Okay, so this means the upload, search, streaming, recommendation, and everything that we create, or we can say the core components of YouTube, would all be part of single cohesive system like this. Okay, or we can have an example just like this also. So this is a application, and in this application we will have the upload, we will have the streaming and other core features if we include them, such as search or recommendation, like, dislike, all of these. Okay, so this would be a single cohesive system. So basically, this monolithic architecture will have all the code base unified, okay? All of the functionality will be tightly integrated into a single application. Now, the advantage of this monolithic can be like its simplicity because it is easier to develop and you can easily test and debug the problems, and faster development if the product is in the early stage, or if the team is small, you can maintain it. But if you have a product like YouTube, which is scaling to the billions of users, you are not going to use this monolithic architecture because of its disadvantage. The disadvantage, the first one, is going to be scaling bottlenecks. So as YouTube scales, a monolithic system could become a bottleneck because this monolithic system could not scale individual components independently, okay? So for an instance, if this streaming feature requires the more resources, the whole system must scale up for it, even the parts that do not need scaling, such as like the search. So this is what we mean by scaling bottlenecks. So like if one of the feature of your product requires to be scaled, the other features like the search, recommendation, likes, dislike, or even the uploads have also to scale, okay? And the second disadvantage is going to be tightly coupled. So basically, tightly coupled means if one change in the system is done, it might affect the other components too, okay? And it is going to be hard to manage and deploy updates without risking the downtime. And then the third disadvantage is going to be slow development. As you scale your product, this will be another disadvantage to your product, okay? So yes, this is what we are going to have for the monolithic architecture. And let's now discuss the microservice architecture. What this microservice architecture does, it breaks the system into smaller independent services. So basically, suppose this is the YouTube. There are different features that we are going to have for an upload, okay? For an streaming, if we have the search recommendation, if we have that core feature, then I'm just taking this as an example, or even the recommendation. And so over here you can see that our system for the YouTube has been broken into the smaller independent services, like for upload, for stream, for search, for recommendations, okay? So if you want to scale the database of the upload, you can do it individually without affecting the stream, search, or recommendation functionalities or the components, okay? And now if we talk about the advantages of microservice architecture, the first one is going to be scalability. And scalability is one of the biggest advantages of microservice architecture because an individual service over here can be scaled independently. So, for example, if the video streaming component is under heavy load, only this service can be scaled without affecting the rest of the other system. Then the second one advantage is independent deployment. You can deploy each service separately in microservice architecture. This means that if the search service needs an update, it can be deployed without affecting the video streaming or the recommendation system. Then we have fault isolation. Since each service is operating independently, if one of the service fails, let's say for recommendation services is failing, it won't affect or bring down the entire platform, and this is going to improve the reliability of the system. So yes, these are the advantages of using a microservice architecture. And now if we talk about the trade-offs between a microservice and a monolithic architecture, we will start with the development speed. For a small team at the early stages, a monolithic architecture can be faster than the microservice architecture. However, if your system is as grown as YouTube, you would definitely need microservice because monolithic could become harder to scale and they can slow down the development process, whilst microservice shine in larger and they have a more complex system where teams need autonomy, okay? Then we have scalability. Monoliths may be easier to scale initially, but at a YouTube scale, the ability to scale each service independently can make microservice a better choice. Then we have reliability. Monoliths are often more vulnerable to SPOF, that is single point of failure, because everything is so tightly coupled into a monolithic architecture. While microservice can provide you fault isolation. Even if one service fails, the rest of the system will continue running. Then we have operational overhead. Microservice comes with a great operational overhead. You have to manage hundreds of services, secure communication and service discovery, and monitor all of the tools and expertise, okay? And the complexity, we know microservices are more complex than monolithic. But just because of the complexity, we are not going to ditch microservice, okay? So like when considering these trade-offs, we are clear that monolithic architecture can be great starting point for the smaller system or if it has a simple application. However, a massive platform like YouTube requires high availability, which we guessed was 99.9% of the time, fault tolerance, and ability to iterate on individual components really quick. Microservice is the preferred choice. Let's now keep going and create a high-level design of YouTube. So at high level, YouTube consists of several layers that work together to handle users' requests efficiently. So first, we are going to have user. User can access YouTube via web or through mobile application, and we are going to call it as a client layer. Then we are going to have like an API layer for exposing endpoints for uploading the video, streaming the content, user management, and many more. So you can even call this API layer as a web server. This is going to be like a front-end server. And these endpoints over here are called through RESTful APIs by the user. Then we are going to have a load balancer. Load balancer is going to help us distribute the incoming request across multiple instances of servers to ensure no single server is overwhelmed. And then we are going to have the service layer. Over here, we are going to have various services which are going to manage distinct functionalities such as video uploading, processing, authentication, recommendation, and notification. So, load balancer will help us distribute the incoming requests to all of these services. Then we are going to have the database. In this database layer, you are going to store users' data, videos, metadata, or comments. Here we can use these combination of SQL or NoSQL database to optimize for different data types. We are also going to have the cache layer, and in this we can utilize the caching mechanism to store frequently accessed data such as videos, metadata, and user session information. And we will also have CDN. So CDN is going to cache and deliver the video content from the servers geographically closer to the user, and this will help us reduce the latency. So this is a high level design of YouTube. This is how it is going to look like at a very high level. And for the cache, you can use Redis or Memcache to store frequently accessed data such as user session, video, metadata, and trending video list. And this will help us reduce the database load and improve the response time. So now if we talk in detail about the video uploading flow, this is how it is going to look like. So first of all, a user is going to watch a video on devices such as their computer, mobile phones, or a smart TV. Okay, then the load balancer will help us distribute the request among various API servers that we are going to have. Every user request except for video streaming will go into the API server. Then we are going to have the metadata database, which is going to store all of the videos metadata. This we are going to shard it and replicate it to meet the performance and high availability. Then we also have the cache. The cache is going to be for better performance. So here you can store user session, trending topic list, or trending videos. You can store it into the cache. Then over here we have the blob storage, or you can say the cloud storage. Blob storage refers to a binary large objects to store the video files in a scalable way. Here, videos are stored into chunks and distributed across multiple servers in the distributed storage system. And the popular storage systems or solutions are Microsoft Azure Blob Storage or Google Cloud Storage or Amazon S3. Okay, then over here we are going to have the transcoding server, which are going to help us convert a video formats to other formats and also convert a video to different resolution. Then we are also going to have the transcoding storage, which is going to store the transcoded video. This is also going to be a blob storage. And once the transcoding is done, we are going to cache the videos into the CDN. We also have the messaging queue over here. This is the message queue that is going to store the information about video transcoding completion events. Then we have completion handler. This is going to consist a list of workers that are going to pull the event data from the completion queue, and this completion handler will help us update the metadata cache and database. And let's now see how the video uploading flow will be like. Videos are going to be uploaded to our blob storage. Suppose we have Amazon S3. Then the transcoding servers will going to fetch the videos from the blob storage, okay? And they will start transcoding the video. And once the transcoding is complete, transcoded video are going to be sent to the transcoded storage, and transcoding completion events will be queued into the completion queue. Then from the transcoding storage, the videos will be cached or stored into the CDN so that it could be available to stream to the users, and completion handler will pull the event data from the queue and it will update the cache and the database. And the API server will inform the user that their videos have been uploaded and they are available to stream so that they can stream the video now. So this is how we are going to have a video uploading flow. And now if we talk about the video streaming flow, this is going to be really simple. Whatever video user want to stream, they're going to request it from the server closest to their geographical location through CDN, and then this CDN will provide them the video that they are asking for, and the video would be ready to stream. How the streaming would be possible because of the streaming protocols. And what are the popular streaming protocol? They are MPEG- or HLS, which is for Apple HLS, and there are many, but this is how the video streaming flow would look like. So in a large scale system like YouTube, the DAG is used to model the transcoding pipelines as a series of tasks with dependencies between them. And what is DAG? It is a directed acyclic graph. A DAG ensures that the tasks are executed in the correct order, and each task output is used as an input for the next one whenever it is necessary. So here is the simplified DAG workflow. Let's see how this works. The first task is the raw video uploaded by the user, after which the video has been uploaded to the blob storage. Then the metadata about the video, resolutions, duration, format is extracted, and this information will help us determine how the video will be processed. Then there will be the job creation. A transcoding job is created and added to the job queue. Here, the job queue will manage the prioritization and distribution to the available workers. Then we have the transcoding to multiple resolution. The raw video over here will be transcoded to multiple resolutions, and each transcoded task happens to be independent but may be scheduled based on their priority. Okay, what did I do over here? So let's take for an example, the 144p transcoding might finish even before the 4K. Right? So this is the work of transcoding servers. Then we have the encoding. Each resolution will be then encoded to the multiple bitrates version. So for instance, the 720p video may have 1 Mbps, 2 Mbps, 4 Mbps versions to support different network conditions. Then we are going to have the segmenting for ABS. The encoded video will be then segmented into the chunks, or you can say would be then separated out into the chunks, and it would be stored into the blob storage. And this is done for adaptive bitrate streaming, and it is done through HLS or dash protocols. So then the transcoded storage and the encoded videos are going to be stored into the blob storage, which is optimized for the fast retrieval and replication across multiple data centers. After it, the video will be then replicated to the various CDN nodes globally, ensuring user can access the video data from the nearest location. And after that, the video would be ready for streaming via YouTube's player, and the adaptive bitrate streaming will dynamically adjust the video quality based on the user's bandwidth. And then for the fault tolerance and scalability in DAG, we are going to have parallel processing. Multiple transcoding and encoding tasks will be executed in parallel. So for example, the 360p transcoding does not have to wait for 108p transcoding to finish, and this will improve the speed and efficiency of the system. Then we are also going to have the retry mechanism. So if any task fails, example the encoding job has failed, the system will retry the task or flag it for manual intervention. So some of the engineers have to intervene it and do something about it. Then we are going to have the DAG execution management. So over here you can use tools like Apache Airflow or similar orchestrators to manage the execution and scheduling of these tasks. And here we will ensure that no circular dependencies exist and the task can be completed into the correct sequence. So now over here we are also going to talk about the safety optimizations with the pre-signed upload URLs. This will enhance the safety, scalability and performance when the uploading videos to platform like YouTube. And what are going to be the pre-signed upload URLs? These are going to be the time limited URLs that are going to provide the temporary permission to upload the files to the cloud storage service without exposing the credentials or requiring direct access to our backend servers. So how the pre-signed URLs is going to work is there is going to be request to upload the video by the client or the user from their mobile application or the web app. They are going to send a request to a server asking the permission to upload the file, and then this server is going to generate the pre-signed URL, which is going to include the expiration time, so like a valid duration like a 5 minutes, and it is also going to have the permission and a specific metadata such as the file type or the size restrictions. Then the client will use this URL to directly upload the video to the cloud storage such as Blob, or you can say Amazon S3 or Google Cloud Storage, without passing through YouTube's application server. And once the upload has been done, the storage server will notify the YouTube's backend server that the video is ready to process for transcoding, encoding, etc. Okay? So by allowing the user to directly upload their videos to the cloud storage with the time limited permission, here YouTube is ensuring that the platforms remain secure and even the scalable while maintaining smooth upload experience for different content creators. So now in the large scale platforms like YouTube, robust error handling is important for maintaining the seamless user experiences and ensuring system scalability. Okay, so these are going to be the types of error in any large scale system that you can see. Like for the client side, you can have the network issue, poor connectivity or timeouts. There are going to be invalid requests such as wrong API use or malformed data. You can even have browser incompatibilities or media playback issues, right? For the server side, you can have high traffic, resource exhaustion such as system overload, okay, and system failure is done, database error, authentication failures, or if your application crashes such as the bugs and unexpected states. You can even have third-party errors or external errors like the issues with the CDNs or the failures with the cloud services like for the storage, API limits, and you can even have the streaming errors such as the buffering time, video quality is dropping, interruptions during the live streaming, and latency issue because of the server load or network problems. So, how we can handle all of these errors gracefully? For it, we are going to have the errors strategies. First of all, we are going to have the user experience, which will display the meaningful messages to the user when the specific features are temporarily unavailable. We can even have retry mechanism. So if an API call fails due to the temporary issue, the system should automatically retry after the delay. And for services such as the video upload, for this the retry should be handled using backoff strategies to avoid overloading the system with continuous requests. Then we are also going to have the fallback mechanism in here. If your particular CDN region is failing, you can redirect the user to the nearest available server. And if the video encoding job is failing, you can rerun it or degrade the quality to ensure the video is still available for streaming. Then you can even have the error logging and monitoring. You can collect and monitor logs across your services using the centralized tools such as Grafana or ELK stack, or you can even implement the alerting system that will notify the engineers in real time for any critical failures or anomalies. Okay, and now if we talk about the fault tolerance design or designing for fault tolerance, so basically over here, fault tolerance in a large scale system like YouTube is about building the system that can handle the unexpected failures in the hardware or the software, and it can be done without the service disruption. So first of all, you can have the redundancy, and here by duplicating the critical components, the system can continue to operate even if one of the service fails. So here we can have the server's redundancy. YouTube must deploy multiple servers into the geographical distributed data centers to ensure that if one of their server fails, the other one can take over it. So, for example, if the video streaming server in Europe or North America and Asia ensures that if one of this region faces the issue, the other server can still serve the users. Okay, then we can have the database redundancy too. We can have the master slave replication or multi-master replication. Then we can even have the database replication and distribution. Since YouTube hosts a large amounts of video content, we need to replicate this content across various CDNs. CDNs will distribute the copies of videos across their server around the globe, and it will ensure the fast access and data redundancy. And if there is an event of server failure in one of the CDN location, in that case, YouTube can automatically route user to another nearby CDN node. Then we have the user data. All the user related data like their watch history or preferences should be replicated into the distributed database. Then we are also going to have load balancing. We can use the global load balancers to route the user's request to the nearest available server or data center. Or we can even have the application load balancer. So at the application level, load balancer will distribute the traffic among the multiple microservices. So if one of the service microservice fail, the load balancer will redirect the request to another instance of the same service. Then we can even have data consistency. We can use eventual consistency or strong consistency for it. And now we can even have a design for high availability. We can have auto scaling. So this will allow the system to dynamically adjust its resources based on the demand. And we can even have multiple region deployments. So deploying the services across the multiple geographic regions will ensure low latency and high availability. And you can even have zero downtime deployments. Basically, high availability system must support zero downtime deployments to ensure that the new updates or changes do not disrupt the user experiences. Okay, so that is what we are going to have for the fault tolerance design and for the high availability design. So if we look over it, we started with the introduction. Okay, we learned about the core features of YouTube, then we cleared the functional requirement for our system design and then the non-functional requirement. Then we went on with the back of the envelope estimations. Here we calculated the total users, daily active users, and what are going to be the storage, servers, capacities. Okay, then we talked about if we want the microservice or a monolithic service. Then we created the high level design of the YouTube. And in detail, we talked about the video upload flow and also the video streaming flow. And then we talked about the transcoding pipeline, how the transcoding works, and the DAG representation. Then we went with the fault tolerance and scalability. So failover mechanism, safety optimizations with the pre-signed upload URLs. Then what are going to be the errors in the system like YouTube, and how can we handle these errors gracefully. We also talked about that. Okay, so that's pretty much all for this video. I hope it helped you, and if it did, then please do not forget to like and subscribe. Also, if you want to see any particular system design video, you can comment that out into the comment section. So I'll see you in the next video. Till then, bye bye and take care.